Hey, on this video we're going to go over the notes on vectors and scalars. So first up, we're going to talk about scalars. A scalar is a quantity that only has the magnitude. So when I say magnitude, I'm talking about the size or the amount of something, and we're also going to include the units that go with it. For instance, if we're talking about mass, we're going to say 5 kilograms, for example. We need the units to be included with it. Temperature, it'd be 21 degrees Celsius, or speed would be a scalar quantity for 65 miles per hour. So you notice all of these things just have a number and the units associated with them. So that's what a scalar quantity is, just the number and the units. Right? Whereas a vector, which is what this unit focuses on, includes both the magnitude and the direction of it. So we're basically taking the scalar and adding direction. So examples include, for instance, for acceleration would be 9.8 meters per second down. We could say a vector quantity for velocity would be 25 miles per hour west, things like that, all right? So now let's go through this list and just determine if it's a vector or a scalar, okay? So the first one, 10 meters, is that a vector or a scalar? If you said scalar, you'd be correct because it doesn't include direction. For the next one here, 51 meters per second east is going to be a vector because it does include direction. For 68 meters per second, also a scalar because there's no direction. For the next one, 8 times 10 to the 8th meters per second is also a scalar because, again, there's no direction included. And then the last one, 60 kilometers down, is a vector because you do have a direction, okay? It's that simple. Just if it includes direction, it's a vector. If it doesn't, it's a scalar. All right, so again, the bulk, all of this unit from here on out is focused on vectors. You just simply need to know what a scalar is for this, okay? But now we're going to focus on vectors and how to solve them. So first up, let's learn a little bit more about vectors. So a vector is represented on paper by an arrow. The length of the arrow will represent the magnitude, and then the arrow will face the direction of motion. And then lastly, a vector can be like picked up and moved on the paper as long as the length and the direction it's pointing doesn't change. For instance, I can take this red arrow and move it all around my screen. As long as I'm not changing which way it's pointing or the length of it, I can move it around, okay? So just to solve this blue box, which the answer is already shown, but which arrow represents a greater magnitude? You'd pick B because that's the longer arrow, okay? All right, a couple definitions you need to know throughout this unit is component vector. It's essentially 2 or more vectors that are acting on the same point. So when we get to word problems later in this video, we're going to be given 2 or more vectors. So the ones given in the question are going to be the component vectors, right? And they're going to all like go one after the next and take you to the end point. Versus your resultant vector is going to be the one vector that has the same effect as the 2 combined vectors. That's what we're going to solve for. It's the result of all those components combined together. So for instance, here I have vector A and B. These would be my component vectors. They're just one after the next. Versus my resultant vector is going to start in the same place and end in the same place. And that's going to be what I'm solving for, is my result. What's the result of these 2 other vectors? Okay? All right, now let's talk about how to give vector directions, because there's a lot of different ways we can do this. For the quantity, again, to be considered a vector, it's got to include the direction that it's going. And there's simple ways we can state directions, such as saying left, right, up, down, north, south, east, west. Those are very easy ways and simple to say. Then there's some complex ways to say direction, and there's 3, probably even more than this, but these are 3 common ones I see out there in physics classes. So the first one is when you use 360 degrees like on a compass, where north is considered 0 degrees. And if you're not familiar with compasses, then this one's kind of hard to use in physics class, right? And I personally don't use a compass in my everyday life, so I don't really like using this one, right? Then there's 360 degrees on a coordinate plane where the positive x-axis is 0. So think of a coordinate plane from math class where your positive x-axis is 0, and then you go like around like a unit circle style, where north would be 90, west would be 180, south would be 270, and then back to 0 at your positive x-axis. This one is is nicer to use because it overlaps with things you've learned in math class and just feels a little more intuitive from bridging to your math class. Then the last one is actually the one we're going to stick with in this class. I don't want to confuse you by using all three. I just want to stick with one. Since these all work, I'm going to just stick with this last one. So this is the one you're going to need to learn how to use, is compass directions, where you're giving the amount of degrees you're going from either the north, south, east, or west axis. And it'll be phrased as a thing of saying like how many degrees, like above or below that axis. So like 30 degrees north of east tells us we're 30 degrees above the east axis. And I'm going to explain that on this slide. So how to use these compass directions. So this example here is 30 degrees south of east. What this means, how to break this down would be that the degrees part tells you how many degrees you're going. The first direction, in this case south, says this is the direction you're going to go from the last one. So in this case, we're going south of the east line, so we're going below the east axis. So if you think of your compass like a coordinate plane, where the positive x-axis is east, the positive y is north, negative x is west, and then your negative y-axis is south. All right. So the last word in the phrase, in this case east, tells us which axis our angle is going to touch. So in this case it's east, so our angle is going to touch that axis. If that said north, our angle would touch north. All right. The first word of it, in this case south, is telling us which way we're going from that axis. So south would be under it, north would be above it. So since it's south, we're going below it. Okay. And then the degrees tells you how far away you're going to go. In this case 30. If it said 50, we'd be even farther. We'd be like right here. Okay, so let's work on some examples. So how would you state the direction of these vectors? So this first one on the left, we have 50 degrees. We're touching the north axis with this angle. So we're 50 degrees and we are to the left of it, or we're towards west over here. So we would say 50 degrees west of north. For the example on the right, we're 40 degrees and this angle is touching the south axis. And we are, again, to the left of that axis, or west of it. So we would say 40 degrees west of south. Okay? All right. Let's do just another check for understanding for vector directions. So we're going to just draw these vectors out. So we have 10 meters at 40 degrees west of south. So we want to touch the south axis. We want to be west of it, to the left of it, by 40 degrees. So that would look like this. All right. For this one over here, 20 meters per second going at 20 degrees north of west. So the axis we want to touch is the west axis. And we want to be north of it or above it by 20 degrees. So it's going to be right here. Okay. All right, now let's move on with solving resultant vectors, and we're going to start with the tip to tail method. So the simple steps for this method is you're going to start by placing any vector with its tail, or the like where you first start drawing the arrow, at the origin or your starting point. Then you're going to place the next vector of any unused vector. So if you have a list of vectors, just another vector, to the tip of the previous one in the direction that you're supposed to go. So if it says you go like to the right, you draw it to the right. If it says to the left, you draw it to the left. Right? Then after placing all of your vectors in the list, or all your component vectors rather, the resultant vector we found by drawing a straight line from the tail of the first vector to the tip of the last vector. So for instance, if my first vector I draw, this would be my tail, this is the tip. So I would draw it tail to tip. Then if my next vector says to go south by a certain amount, I start where the other one ended. So this one ended here, and then I go tail to tip. All right. And then if my next vector says go to the left by a certain amount, I go that direction again, starting where I left off and ending. Then my resultant vector is going to connect from where I originally started to where I ended. Okay. All right. So with one-dimensional vectors, which means they're all going the same way, like left and right, up and down, they're just going like back and forth kind of thing. So when they're going in the same direction, we can just simply add them together. So for instance, if I have one going 10 meters east, and then my next vector goes 5 meters east, these are going to combine where my resultant vector is just simply 15 meters east. Right? When they're going in the opposite direction, for instance, if I have one going 8 meters west, then one going back 3 meters east, my resultant vector is still going to be from where I started to where I ended. So mathematically, I'm just going to simply subtract. All right. And so that's one-dimensional vectors are pretty easy, right? For ones that are in two-dimensional, for using this method, it gets a little more complicated and a little more tedious, and it can become very time-consuming. So when you solve things in 2 dimensions, so it would be like this, where you've got multiple vectors and they're going at angles. They're not just simply going like left and right or up and down. It gets really complicated here to solve this. You do have to use a ruler to measure out each vector, and you have to use a scale. For instance, if this said like this first vector was 100 meters, you can't fit that on your paper. You've got to scale it down, and you've got to keep that scale consistent amongst all your arrows. You will also have to use an angle to draw your, use a protractor to draw your angles. For instance, this vector right here is at an angle, and you've got to measure that precisely. So if it says you're going 45 degrees south of east, you've got to make sure it's exactly 45 degrees, right? And protractors, sometimes they're just confusing to use. You may not want to always use them. And then to find your resultant vector with these vectors, we've got to measure this angle too to figure out which way that's going. So it's not the friendliest of methods to use. It is possible. We're gonna also learn how to solve them mathematically when they're this complicated. That normally gets you your answer a lot faster than having to get out a ruler and a protractor. Okay. All right, let's move on to something else, which is solving them by when they form right triangles. So this is going to overlap a lot with what you've learned in previous math classes. So this, again, only is going to work with right triangles. So the first step you're going to do is always on any vector problem is going to sketch out your vectors, all right? And when you sketch this out, you're going to see you get a right triangle, and that's how you're going to know to do these steps. And these are the simplest of the vector problems that we can get. Well, I guess second simplest after them just going east and west kind of thing in the one dimension. So your first step, once you've sketched it out, is to then find the magnitude, and you're going to do this by using Pythagorean theorem, which, as a reminder, is a squared plus b squared equals c squared, where a and b are the sides of your triangle and c is your hypotenuse, right? Then you're going to use, your last step will be then to find the direction, and you're going to use a trig function to do this, as well as include the compass direction part. So for your trig functions, hopefully you've learned these before, but if not, they're sine, cosine, and tangent. These are the normal ways of writing them. But in our case here, we're going to solve for the degrees, which in this case was represented with theta. So we're actually going to want to use the inverse trig functions for this. We're going to commonly use inverse tangent for a lot of these. Technically, you can all use any of them, but I tend to lean towards the inverse tangent. So inverse tan and then opposite side over adjacent side equals your angle. So just to review what opposite and adjacent sides are. So if my angle is here, my opposite side is the one across from that, and my adjacent side is the one that's touching the angle. And then our hypotenuse is the side that's slanted, which is across from your 90-degree angle. All right. All right, let's work on an example. So our first example has an object that's moving 400 kilometers per hour north, and then it goes 300 kilometers per hour west. We want to find the resultant, and just as a reminder, that includes both magnitude and direction. Right? So our first step is to sketch it out. I've already got a picture drawn here of 400 kilometers per hour north and 300 kilometer hours per west. And then my resultant vector is going to connect from where I started to where I ended. Okay, so I want to find the value of r. I've labeled that as my resultant vector, and I also need to find this angle here to include with my direction. Right, so we're going to use Pythagorean theorem. We're going to plug in 300 squared plus 400 squared because those are the legs of my triangle, and that equals r squared. So when I add up in the calculator 300 squared plus 400 squared, that's going to give me 250,000 equals r squared. So then to get just r is what we need. We're going to square root both sides, giving me an r value of 500. So my magnitude is going to be 500, and the units that are going to go with it are the same ones that I had in the problem, which in this case is kilometers per hour. So my magnitude is 500 kilometers per hour. Next up, I need to find my direction it's going. So first part of my direction is going to be the angle of this. So to do that, I'm going to use an inverse tan of 300 over 400. So my opposite side is 300. My adjacent side touching to that angle is 400. That's going to equal theta. And when I plug that in the calculator, I'm going to get 36.9 degrees. Right? So then the last part to include is this angle is 36.9, but I need to say whether it's, east of south or south of west. And in this case, this arrow right here is pointing straight north, and I'm going to the left of it or west of it, so I'm going to be west of north. So my full final answer is going to be 500 kilometers per hour at 36.9 degrees west of north. So that's the final answer that I want here. All right. All right, for my last example, we're going to solve a right triangle problem, but we're not going to solve for the hypotenuse this time. We're going to solve for one of the legs of the triangle. So in this example, a tiger walks 8.485 meters at 45 degrees south of east and then goes 6 meters west. We want to find the resultant vector. And I'm just going to remind you that it will form a right triangle. So when you're sketching this out, you know for sure you've got a right triangle. So my sketch, I'm going to go 8.485 meters at 45 degrees south of east. So I'm going to draw that in that direction. And then I'm going 6 meters west. Okay, so at the end of that one, I'm going west, and I know this is going to form a right triangle, so I know my resultant will go straight down, so this forms a right angle in that corner. Okay, so this is my 90-degree right angle. All right, so let me label those real quick. And now we want to solve for our magnitude. So we can still use Pythagorean theorem, but in this time, instead of solving for C, we're going to solve for one of the legs. So in this case, I left B alone, and we're going to solve for B. So we're going to square both numbers. So we have 36 plus B squared equals 71.99. And then we can subtract the 71.99 minus 36 equals b squared. So when we subtract that, it happens to round to 36. So it's 36 equals b squared. And then we want to square root both sides to get our leg of our triangle is 6. So both legs of this triangle in this case is 6. All right. Now for direction, we want the direction of this red resultant arrow. Okay. We want which way is this going. So we don't care about this angle here. We already know that angle. We know it's 45 degrees right here. We want to know which way this red arrow is going, and just by simply looking at it, we know this arrow is going straight south because we need a 90-degree angle here. So to make that, we know this one has to go south. So our full final answer is just 6 meters south. Now I'll give you a hint. When we have problems like this on a quiz or in test in this class, if you're given a problem in here where you're solving for one of the legs of the triangle, your direction for that leg is either going to be north, south, east, or west. It's not going to have a degree. Technically, we can rotate this triangle so it's not perfect, like the legs aren't going perfectly north, south, east, or west. But to keep things simple and straightforward, I'm going to make sure that it's always that case in here. Since this is just an intro to physics class, it's going to go north, south, east, or west. Okay, when you're solving for the leg of a right triangle. All right, we're not going to overcomplicate things. But anyway, that's the end of this video notes. Please let me know if you have any questions or need any help.